We're going to continue our exploration of equilibrium in molecules by looking at solubility and equilibrium constants. Our learning goals are to use these constants to determine an equilibrium condition, that is, the concentrations of reactants and products that need to be present in order for a certain system to be equilibrium. Now you'll recall that the general reaction, if we just use the abstract A plus B goes to C plus D, would have an equilibrium constant that would look like this, where each of the product concentrations are in the numerator, the reactant concentrations are the denominator, and all of the concentrations are raised to the power of their coefficient in the balanced chemical equation. So just to clarify with the reaction we've been looking at for the last few videos, NO plus Cl2, this would be the equilibrium constant in that case. The product is NoCl2, so it's in the numerator. The reactants are NO and Cl2, they're in the denominator. And all of the coefficients are 1, so this is a pretty simple one. I want to ask, what about a reaction like this, where you got calcium carbonate converted into calcium oxide and carbon dioxide? This is the conversion of limestone to lime that generates carbon dioxide. Would we have an equilibrium constant that would be given by this, the concentration of calcium oxide times the concentration of carbon dioxide divided by the concentration of calcium carbonate? But how do we define these? Both of those substances are solids in this reaction, so what is their concentration? Well, it turns out there's not really a concentration we give it, and in fact that concentration does not change as this reaction occurs because it's just a solid. So we consider this to be a heterogeneous equilibria. That is, it's a chemical reaction that involves multiple phases of matter. A gas in carbon dioxide and two solids in calcium carbonate and calcium oxide. And now, whenever we run into this, it's customary for us to set the pure solids and liquids, set their concentrations equal to 1. In effect, what's really happening is their influence in the reaction is sort of subsumed into the equilibrium constant. And it's only the fluid phases, like gases or solutes in a solvent and in a solution, that are going to vary during the course of a reaction. So that means that the equilibrium constant for this calcium carbonate reaction would actually just be the concentration of the CO2. Now this turns out to be very helpful when we're talking about equilibria for things dissolving. So remember, lead sulfide is insoluble salt, but it's a matter of degree. So we have a solubility equilibrium for lead sulfide that looks something like this, where the solid lead sulfide is in equilibrium with lead ions and sulfide ions in aqueous solution. So if we use the fact that the solid is going to just appear as 1 in the equilibrium constant expression, then our equilibrium constant is just going to be the product of the concentrations of lead 2 plus and sulfide 2 minus. We actually have a special name for this equilibrium constant. That's why I've used an SP subscript for it. We call it the solubility product constant. And for anything that is dissolving in a solution, into a solvent, that starts as a solid, that solid is going to appear as 1 in the equilibrium constant, so the only things that will appear are the product solutes in solution. That's why it's always going to be a product of things and there's nothing in the denominator. So we can use this to actually solve some things about solubility. So for example, I may be interested in knowing what is the concentration of chromium ion in chromium hydroxide when it's dissolved in water. Now, chromium hydroxide is not a very soluble compound, but a little bit of it will dissolve. So this is the solubility equilibrium that we have, and this would be the expression for the solubility product constant. Okay, notice that it is the product of the two ions that are formed in solution. The hydroxide ion concentration is squared because it has a coefficient of 2 in the balanced chemical equation. Now it turns out that the solubility product constant for this is 1 times 10 to the minus 17. Whenever you have a very small value there, it means that not very much of it could dissolve. But we're going to figure out exactly how much of it did. Now notice that whenever chromium hydroxide dissolves into water, it's going to form 1 chromium 2 plus ion and 2 hydroxide minus ions. So I know that whatever amount that is, I'm going to have twice as much hydroxide ion as I'm going to have chromium ion. What I want to do is solve for how much chromium ion is in the solution. So now I simply substitute x and 2x in for those two concentrations in the expression for KSP, which means that I've got 4x cubed. And the mathematical equation that I'm going to need to solve is 4x cubed equals 1 times 10 to the minus 17. So now if I solve that, I would find that, in fact, x is equal to 1.4 times 10 to the minus 6 molar. So it's really a very slight concentration that represents the chromium ion in this particular solution. Now, another thing that we can do with equilibrium states is explore how much they are affected when we change concentrations of things that are at equilibrium. So, for example, let's suppose that I have an NaCl2 reaction system that is at equilibrium. So all of the concentrations obey the expression shown here. Kc is equal to NaCl2 divided by NO and Cl2. And now I want to adjust the concentrations, but I'm going to do it in a particular way. And let's say I can snap my fingers and make this happen magically, so there's no difficulty in making this happen. But I'm going to take the NO that's present in there, and I'm going to cut it in half. And I'm going to take the Cl2 that's present in there, and I'm going to double it. So I'm just going to snap my fingers and make this happen. And I'm not going to change the NoCl2 concentration at all. So this is going to represent a new combination of things in the reaction state. But I want to point something out. If I look at the product of my new concentrations of NO times Cl2, then I'm going to use the expressions that I got above. So I'm going to plug those in, and I'm going to get that's equal to 1/2 times NO at the equilibrium level, equilibrium value, and 2 times chlorine at the equilibrium value. But then when I multiply this out, I'm going to end up having 2 times 0.5, which is just 1. So in fact, the product of the new concentrations of NO and Cl2 is just equal to the product of the old concentrations that were at equilibrium. I didn't change the NoCl2 concentration, so in fact the value of that quotient that's shown up above is still the same. It hasn't changed at all. This now represents a new reaction state. It's still at equilibrium, but it's in a different equilibrium state. The whole point of doing this was basically to drive home the notion that even though there is only one equilibrium constant that specifies this reaction, there are an infinite number of possible combinations of concentrations that will satisfy that equilibrium constant expression. So it's useful to know and not get hung up. There's not just one equilibrium condition. There are an infinite number of equilibrium conditions, and we have just seen 2 of them for this particular reaction.